Hello everyone! Welcome to the Summer of Math Exposition. My name is Ben, and today we'll talk about listing the rational numbers. Let's get started. To practice listing the rationals, let's try to solve a puzzle together. The challenge is this. Can you make a list of all the rational numbers exactly once each? You may have heard before that the rationals are countable, so with an infinitely long list, there should be enough room for each rational once. So let's give this a try. We might start with 1 over 1, then 1 over 2, 1 over 3, and so on. But if we continue like this, we would use up the entire list and never see fractions like 2/5, for example. Clearly, we need to be more creative. Let's put this puzzle aside for a minute, because I have something related to show you. We'll start with a fraction p over q, where p and q are positive integers. There are two simple operations we can perform on this fraction to get new fractions. We could add the numerator to the denominator, or we could add the denominator to the numerator. These operations will be important, and I'll call them the left rule and the right rule. Let's see what we get when we apply these operations to the fraction 1 over 1. From the left rule, we get 1 over 1 plus 1, which is 1/2. And from the right rule, we get 2 over 1. And we can apply these rules again to get more fractions, and so on. This structure is called a tree, and this one is called the Calkin-Wilf tree, named after the mathematicians who discovered it. This tree has two special properties. First, every fraction in the tree is reduced. In addition, every possible reduced fraction will appear somewhere in the tree. Because of this, if we read off the tree one row at a time, the list of fractions will be a solution to our puzzle from before. This list is called the Calkin-Wilf sequence. It has a recursive definition which looks like this, but the main question we'll answer today is, can we compute the terms of the sequence directly? The answer is yes, and to do this, we'll revisit the tree. Here's the Calkin-Wilf tree from before, and next to it, we'll make a new tree. At each node, we'll label the term number of its corresponding fraction in the sequence. So 1 over 1 is first, then 1 over 2, and 2 over 1, and so on. This tree represents the position n in the sequence. What are the generating rules for this tree? They're simply 2n and 2n plus 1. Computer programmers may recognize these as important operations in binary, so to make this tree more meaningful, let's rewrite the nodes of this tree in base 2. I'll denote that with n subscript 2. And now we can interpret the rules as appending a 0 to go left and a 1 to go right. Bringing back the original tree, we can now use n as directions for getting to L of n. I'll put start tokens outside of the trees for no n. Now we can enter the tree by appending a 1 and going right. We could go right again to n equals 3, then 7, and 14. We see that L of 14 is 3 over 4, and we used 14 in binary as directions to get there. But we don't really need to make the trees to do this. All we need are the rules. Let's use the same example, n equals 14. We write n in binary, and then we use the n-tree rules to determine when to go left and right. Finally, we can apply the left and right rules from the start token, first to 1 over 1, then applying the right rule twice more, and finally the left rule, to get to 3 over 4. And this is the 14th fraction in the sequence. This process was faster, but we still had to perform the left and right rules one at a time. So let's see what multiple moves in a row look like algebraically. Here I'm showing m right movements in the tree. We begin at p over q and apply the right rule m times. This simplifies nicely to m plus p over q. On the other hand, we can take m left movements by adding p to the denominator m times. This doesn't simplify right away, but the trick here is to invert the reciprocal of this fraction. Now it simplifies, and we'll do another double inversion to get this in terms of p over q. Okay, let's see what happens when we combine these two types of movements. Here are the two rules we just determined. And at the bottom of the diagram, we see that P over Q is m right moves away from its ancestor, P prime over Q prime. But we also know how to express this using our new rule, so we get this equivalence. The same thing is true here in the middle with left movements, and we get another equality. And we can substitute this value in, and then we can write P over Q double prime in terms of its ancestor, and so on. The result is surprisingly simple. We can write P over Q as a continued fraction where the elements down the side are the number of left and right movements in the tree. Pretty cool. Now I'll show you an example of how much easier this is than before. We'll use 49 as n, then write n in binary, and this time we'll split the number into groups of consecutive ones and zeros. Then instead of evaluating the left and right rules, we just have to write these numbers as the elements of a continued fraction, and evaluate. So the 49th fraction in the sequence is 9/7. And this is not all we can do. Here are the steps we just took to get from n to L of n, and the key insight here is to realize that all of these steps are reversible. So we could start with a reduced fraction like 9/7, then write it as a continued fraction. I'll explain how to do that in just a minute. Then we use the coefficients down the side to write ones and zeros, and then we treat this as a binary number and convert it back to decimal. This is huge when it comes to listing algorithms because we can answer two important types of questions. A forward question, like what is the 49th element of the sequence, and a lookup question, like where does 9/7 appear in the list? What's special is that we are using the same method for both, and that's what's so powerful about using continued fractions. Now that we've covered the main result, I'd like to show you a few more things that we can do with the Calkin-Wilf tree. Here's the right half of the tree. You'll notice that I pruned off the left branch of 1/1. What I want to show you is that this tree has a very close relationship with the Euclidean algorithm. This algorithm uses the fact that we can write a larger number a as some multiple of a smaller number b with some remainder r. To demonstrate what happens, let's focus again on 9/7 at the bottom of the tree. Look what happens when we perform the algorithm on 9 and 7. Right away, we notice that the multiples 1, 3, and 2 are the number of left and right movements in the tree. And if we look closely, we'll see that the values of b and r can be found as the numerators and denominators of the fractions at the turning points. The other thing to note is that when the algorithm stops, this number here is the greatest common divisor of the original two numbers. Here it's 1, and we should expect that because all of the fractions in this tree are reduced. And since the q's represent the number of movements from the start token, they are also the continued fraction elements of 9/7. So this is one way to compute them. Now, that algorithm seemed to move up the tree, so as a last interest, I'd like to formalize what these backward movements are and explore what they can do. Here's the familiar picture of the left and right rules. Algebraically, we can undo these rules as follows. To make a backward right movement, we subtract q from the numerator. And to make a backward left movement, we subtract p from the denominator. The Euclidean algorithm finished at the start token, but let's see what happens when we try applying these new rules to go even further. Here's the Calkin-Wilf tree, and if we take a backward right step from 1/1, we see that our start token is actually 0/1. But we can go further. Another backward right movement takes us to -1/1, and here's where it gets interesting. More backward movements get us here and here, revealing the Calkin-Wilf tree upside down and all negative. This is really beautiful, and what's nice is that this full tree has symmetry around 0. By reading off the rows of this new double tree, we get a sequence which I'll call the extended Calkin-Wilf sequence, and this is a true solution to our puzzle because it includes all of the rationals, positive, negative, and 0. With this, I'd like to close by showing you that the terms of this sequence can be found using the binary method from before, with a slight tweak for negative numbers. We'll compare n equals 49 to minus 49. Originally, we wrote n in binary, and we'll do the same here, except we're going to distribute the negative to each of the place values. I'm using vertical bars to separate the place values, but this is still one binary number. Now, we're supposed to group the ones and zeros, and here they are negative. You can think of them as groupings of backward movements. Then we make these the elements of a continued fraction, and it evaluates to 9/7. The negative one should therefore be minus 9/7, and so it should be the negative of this continued fraction. But there's a nice property that multiplying a continued fraction by -1 is equivalent to making each of the coefficients negative. By doing so, we see the clear symmetry as the negative groupings are the negative coefficients. And that's it. Before we close, I'd like to show you an example of how these results can be put to use. We'll focus on the Fibonacci numbers, which is a list of numbers generated by the rule that the next term in the sequence is the sum of the previous two terms. If we begin with a ratio of the first two Fibonacci numbers and apply the right rule, we can simplify the result using the relation. Then applying the left rule, we can do the same thing. And this will continue as we alternate left and right. In the Calkin-Wilf tree, we see those Fibonacci numbers appearing here, beginning at the start token 0/1. The pattern is to notice is that after k movements down the tree, ending with a right movement, we arrive at a ratio of Fibonacci numbers whose limit as k goes to infinity is the golden ratio. Let's apply what we know about the terms in the Calkin-Wilf tree. If we arrive at the golden ratio infinitely far down the tree, then we know that the value of n is produced by alternating left and right movements. We don't really care about the value. All that matters is the alternation of movements, one at a time. From this, we can write L of n as this continued fraction. But L of n is the golden ratio, so these are equal. What we get is a continued fraction expression for the golden ratio with hardly any effort. Pretty neat. So that's all I have for you today. I really hope you enjoyed. A huge thanks to Grant for organizing this math exposition, and thanks to you for watching along.